Welcome to DP Tutorials by Donny Jarwa. In this teaching module, we will emphasize on one topic, which is the combination of resistors, and over here we will learn two cases for the combination of resistors. Number one will be in series and number two, which will be in parallel. So this teaching lesson is very intriguing in the sense that it finds application in most sophisticated electronic devices and basic electronic circuit connection. So in this case, we will consider three resistors having resistance R1, R2 and R3 respectively, and all these resistors are connected across a battery having a potential of V volts. Now we already know that when we have a battery will always have two polarities, okay, the positive polarity and the negative polarity, plus and minus. And over here let us place this key, okay. This key will make the circuit to behave as an open circuit as well as a closed circuit. Now over here, if I have a key will be represented in this form. This is the symbol of a key in an open circuit, and this will be the symbol of a key in a closed circuit, okay. Also, we can have different types of representation for the key. This will be for the closed circuit, and this will be for the open circuit. Another symbolic representation of a key in no, this is quite wrong. Okay. This will be the symbolic representation of the key in an open circuit. This will be the symbolic representation of the key in a closed circuit. So another representation, this will be the symbolic representation of a key in an open circuit, and this will be the symbolic representation of the key in a closed circuit. Okay. So these are some of the important applications. These are nothing but symbols related to what? Related to a key. Now over here, when we have this battery, we know that this battery will be sending electric current through all these resistors, and keep in mind that when these resistors are connected in series, okay, the same amount of current will flow through each of the resistors, okay, So over here, that means if I is that current which flows through the resistors, so over here let I be that current. So capital I will be the current flowing through all these resistors, but which means that all the current I which flows to all these resistors will be the same. It might be that if 2 amperes of current is flowing through this network, that means same amount of current having 2 amps will be dropped on this resistor having different ohms R1, R2 and R3. But accordingly the potential difference across all these resistors will be different, which means that V1, V2 and V3 will be the potential drop across R1, R2 and R3 respectively. So for here, which means that the potential drop on R1 will be V1, the potential drop on R2 will be V2, and the potential drop on R3 will be V3. So from here, we need to know what is the value of R1, what is the value of R2, or what is the value of V1, what is the value of V2, and what is the value of V3. We can do that by using the basic relation of Ohm's law to find out what is the potential. Okay, what is the potential across V1, V2, and V3. So this is our key idea. So from here, let us write down the potential V1. The potential drop V1 across the resistor R1 is given by this relation. Okay, V I R1. Okay, and then V2 will be I R2, and then V3 will be I R3. V3 will be I R3. And then from here, that means if I mark this point as point A, and if I mark this point as point B, that means we have to find what will be the total potential across the junction points A and across the junction point B. So in order to find the total potential of all the resistors to these given points A and B, that means let V be that potential. Okay, let V be that potential, or we can write as Vs. Suppose from here, that means the total potential will be the addition of all the potentials, to each respective resistors. So from here, that means over here this will be I R1 plus I, okay, I R2 plus I R3, which means from here that I is common, so we can write this as I R1 within the bracket. That means we have this expression. Okay, within the bracket we have this expression. So this will be V. That also will be V. Okay. Then since all these resistors are connected in series, okay, they are connected in series. So let the potential be Vs. Okay, we will write this as okay, we will write out that afterwards. Since the potential be Vs. Then from here, if Rs be the effective resistance, okay, if Rs be the effective resistance of all those resistors which are connected in series, then that means the potential, okay, the potential V, that potential V will be equal to 1, will be equal to IRS. Okay, that potential V will be equal to IRS, which means that V is nothing but 1. V is nothing but the total potential. Okay, V is our total potential. And if V is our total potential, so if I mark this as equation number 1, if I mark that as equation number 1, equation 1 reduces to the following expression. Okay? Equation 1 reduces to the following expression. So if I mark this, I can take this I to the denominator of the right hand side, which means that V divided by I is nothing but 1. V divided by I is equal to Rs. So from equation 1, okay, equation 1 implies that V divided by I will be equal to that bracket term, which is equal to R1 plus R2 plus R3, which means, okay, from here that this will be equal to 1. This will be equal to Rs. This is the term. V divided by I will be equal to Rs. So over here we will write Rs, that means resistance in series. When all the resistors are connected in series, the effective resistance will be the algebraic sum of all the three resistors. Okay, of all the three resistors. From here, it is very apparent that when resistors are connected in series, the effective resistance will be the algebraic sum of all the individual resistors, which means that if three resistors are connected in series, it is the total sum of R1, R2 and R3. Now, if there are n resistors, which means that Rs, if there are n resistors, that means there will be summation of I equal 1 up to n, then this will be equal to 1, equal to Ri, for n number of 1, for n number of resistors, Now from here we can come to the conclusion that when the equivalent resistors, the equivalent series resistance is equal to 1, the algebraic sum. This is the very important word, algebraic sum of the individual resistor. Mind you, this conclusion is very important for examination point of view. And remember that while doing the lab session also, we will do some experiments based on to prove the total resistance when resistors are connected in series or when resistors are connected in parallel. Another important form is we will learn about resistors which are connected in parallel. When resistors are connected in parallel across a voltage source, okay, that means over here we have this battery having two polarities, plus and minus, and in this case this circuit will be connected across via this key. But when you have this symbol like this, that means this is simply, okay, this is initially the circuit is an open circuit. Okay? Initially, the circuit is an open circuit. But, okay, but when you want the current to flow in the entire circuit, that means you have to close the circuit. So you have to put that point. Okay? When we insert that key, that means that point, the circuit is no longer the closed circuit, but the circuit in this case is said to be a closed circuit. Always remember that current flows in a closed circuit, not an open circuit. Previously, okay, previously also in this case, when the current I, okay, when the current I is flowing on that circuit, that means this key should be closed by inserting that one-way key. That means this is the open, or this is a closed circuit. Okay? This is a closed circuit. Current always flows in a closed circuit. Clear? So from here, when these resistors are connected in parallel, when resistors are connected in parallel, always remember that the potential through all the resistors will be the same. Okay? The potential through all the resistors will be the same. Okay? So that is the most important key feature. That means when resistors are connected in parallel, that means across the battery, they will be having what? The potential V. Then they will be having the same potential. Okay? Same and equal potential drum is maintained towards all resistors, which means that if capital V, okay, if capital V is the voltage from the source, which means that the voltage across V1, the voltage across R1, the voltage across R2, the potential across R3 will be equal to what? Will be equal to this potential V from the voltage source. And from here, accordingly, the current in the main circuit, this is the main circuit. If I name this as point A, and if I name this as point B, okay, the current in the main circuit, that current will be what? That current will be I. I is the current in the main circuit. This current I in the main circuit, the moment that it enters this junction point here, the moment that it enters the junction point here, that means that current will split, okay, into three branches. First branch, the current flowing to the second branch, and the current flowing to the third branch. So all these currents will move across the individual resistors. So over here, we have make an assumption that let I1, I2 and I3 be the current passing through the resistors, having resistance R1, R2 and R3 respectively. So from here, let that resistance, okay, let this current I1 be the current flowing across branch across the first resistor, I2 be the current across the second resistor, and I3 be the current along one across the third resistor. So accordingly, over here also, by using Ohm's law, we have to determine our target over here is that we have to determine I1, we have to determine I2, and we have to determine I3. So this is our target. We don't know. Like for example, suppose if the current in the main circuit is 3 amperes, and if the voltage, suppose if the voltage is around 1.5 volts, if the voltage is around 1.5 volts, then I1, if you add I1 and I2 and I3, it should be equal to what? It should be equal to 3 amperes. So we have to find out the value of the individual currents through the resistors. So we can find out I1, I2 and I3 by using Ohm's law, okay, by using Ohm's law relation. So using Ohm's law relation, we can find out what is I1, what is I2 and what is I3. Accordingly, then from here we can write in this way: the voltage across the resistor R1 will be I1 R1, which implies that this value of I1, we are interested in finding I1, so we will write I1. I1 will be equal to 1. I1 will be equal to V divided by R1. Similarly, the voltage across R2, okay, the voltage drop across this R2, it will be equal to 1. It will be equal to product of current into resistance. I2 into R2 will give you voltage. I2 into R2. So what is this I2? This I2 will be equal to 1. This I2 will be equal to V divided by 1. V divided by R2. Similarly, the voltage across the resistor R2. I3 into R3. So product of current and resistance is nothing but voltage. So from here, this current I3, will be equal to V divided by I3. Now next step, we have established all these values of I1, I2 and I3 respectively. So then if we add all these values of the current, then from here, therefore total current, therefore the total current is this total current is given by the total current is given by, then it is given by I. Now when you look from that figure, that means that current I will be equal to 1. That current I will, this current I in the main circuit will be equal to the addition of 1, will be equal to the addition of I1 plus I2 and plus 1 plus I3. Keep in mind that all this is what is learned, what we also know as our Kirchhoff's law. We will delve about this in the later section. This is also known as our Kirchhoff's first law or Kirchhoff's current law. Okay? This is also known as the Kirchhoff's first law or the Kirchhoff's current law. Okay? Then from here we can also write down this value of the independent values of I1. What is I1? I1 will be V divided by R1 plus V divided by R2 plus V divided by 1. V divided by R3. So V is common. Then we can take outside. Then we are left with 1. 1 divided by R1 plus 1 divided by R2 plus 1 divided by R3. So 1 divided by R3. So from here, we can mark this as our second relation, equation number 2. Equation number 2. Then from here, since all those three resistors are connected in parallel, let Rp, let Rp be that effective series, effective parallel combination. If Rp is the effective parallel combination, which means that the voltage, the voltage will be, the voltage V will be 1, will be I R P. Okay, what is this voltage? Voltage V, this voltage V, V and I will be Rp. Then from here we can write, we can write in this form. That means over here V divided by I will be, V divided by I will be equal to Rp. V divided by I will be equal to Rp. Or 1 by Rp, the reciprocal of 1 by Rp, that means it is equal to 1. It is equal to I divided by V. Now from equation 2, we have, V is on the left hand side and I is on the right hand side. We will cross multiply that V. We have this equation of 1 by R1, this expression of 1 by R2, and we also have that expression of 1 by R3 in the bracket, term inside the bracket. We'll cross multiply this V to the denominator of this right hand side, then we get this term. But over here we can ponder from here that this term of I divided by V, this term of I divided by V is nothing but 1. It's nothing but 1 divided by Rp. 1 divided by Rp. So this will be 1 by R1 plus 1 by R2 plus 1 divided by Rp. So this is the expression for the total resistance when resistors are connected, in parallel, which means that the total resistance will be equal to the sum, algebraic sum of the reciprocal of the individual resistors, algebraic sum of the reciprocal of the individual resistors. So from here, which means that this total resistance, the total resistance will be equal to 1. The total parallel, the total parallel resistance, is equal to 1. Is equal to the this equal to the individual is equal to the algebraic sum. It is the algebraic sum of the reciprocals, okay, of the individual resistors of the reciprocals of the individual resistors, okay, of the individual resistors. All right, in short, of the individual resistors. Which means that if there are n resistors in this case, that means it will be 1 by Rp, which will be equal to summation of I equal 1 up to n, okay, summation of I going from 1 up to n, and this will be 1 divided by Ri. So this is our expression for resistance in parallel, okay, when resistors are in parallel. Now some of the key points or the summary that we have to know from here is that what type of combination will give us more resistance, either when resistors are connected in series or either the resistors are connected in parallel. Suppose, okay, we'll take an example, and then let the value of R1 will be equal to 1 ohm, the value of R2 will be equal to 2 ohms, the value of R2 will be equal to 2 ohms, the value of R3 will be equal to 3 ohms. Then from here, if resistors are connected in series, which means that it is the algebraic sum of the individual resistors, okay, then over here this will be equal to 1 plus 2 plus 3, and the total resistance will be equal to 1. The total resistance will be equal to 6 ohms. Okay, the total resistance will be equal to 6 ohms. What is our conclusion from here? When you look at the value of Rs equal to 6 ohms, which means that the total resistance Rs is very, very large than the largest resistance. This R3 having the value of 6 ohm is the largest resistor, okay? The largest resistor having the largest resistance, and this R1 having resistance of 1 ohm, this is the least resistor, which means that if all these three resistors having 1 ohm, 2 ohm and 3 ohm are connected in series, so the total resistance 6 ohms will be very, very greater than the largest resistance, okay? Will be greater than the largest resistance. So if the resistors are connected in series, so which means that the total resistance will be greater than the largest resistor. So the total resistance will be greater than the largest resistor. Will be greater than the largest resistor. And moreover also, the total resistance of the circuit will be more, okay, which also implies that total resistance of the circuit is large. The total resistance of the circuit will be large. Is large. These are the two peculiar points that we need to understand. Now, what happens if these three resistors are connected in parallel? The expression for parallel combination is that it is given by 1 by Rp equals 1 by R1 plus 1 divided by R2 plus 1 divided by R3. Then we will substitute accordingly. That means in place of R1 it is 1 ohm, in place of R2 it is what? 2 ohms, okay? In place of R2 it is 2 ohms, and in place of R3 will be 3 ohms. So from here we'll do the usual mathematical analysis, whereby we have to take the LCM. The LCM of 1, 2 and 3 is what? The LCM will be 6, and over here this will be equal to how much? 1 divides this will give you 6, okay? 2 divides 6 will give you 3, and this 3 divided 6 will give you 1, will give you 2. So 6, 7, 8, 9, 10, 11. So this value, okay, this value over here will give you 11 by 6, okay, 11 by 6, which means that 1 divided by RP will be equal to what? 11 divided by 6, 11 divided by 6 ohms. But we want to find RP, so we take the reciprocal of it, so it will be given by what? 6 divided by 11. So 6 divided by 11 ohms, and the value of 6 divided by 11 ohms, yeah, this is the value of 6 divided by 11 ohms will be approximately equal to 2.545, okay, 2.545 ohms, which is very small, okay, which is very small. That means, okay, that means this when resistors are connected in parallel, which means that this value of 0.54 ohms or 0.55 ohms, it will be very small, very small than the value of R1, which is equal to 1 ohm. So when that means the total resistance in this case, the total resistance, or therefore that means RP will be less than R1. Okay, RP will be less than R1. So this is the most important, the important conclusion with regards to total resistance in series as well as in parallel. So from here, what happens is that the total resistance, will be smaller. Okay? The total resistance will be smaller. Than the least resistor. And conclusion number 2 is that the total resistance will be smaller. The total resistance of the circuit, the total resistance of the entire circuit, is small. The total resistance of the entire circuit is small. So in most certain cases, for electrical household wiring system, we prefer less resistance. Okay? For household circuit, keep in mind that these combination of resistance are very important for household wiring circuit. Okay? For household circuit, in household circuit or for electrical wiring system, we prefer parallel connection. Why we prefer parallel connection? The basic importance of parallel connection is that it offers what? It offers the least resistance. It offers least resistance. And when the resistance is small, the heat is also small. Okay, when resistance is small, it implies that the heat developed from this, the heat also will be small. And if heat is small, that means these electrical appliances will last long. Okay, all those electrical appliances will last long. The electrical appliances will last long. It will not burn. Okay, and it will sustain for a longer period of time. So these electrical appliances, what will happen to these electrical appliances? like room heater, electric bulb, the electric fan, all these electrical appliances, they will last long. They will last long for a certain period of time. So these are the applications of these combination of resistors. Just go through these lectures so that you will have a clear concept about how to do the analysis of this problem. Okay? Thank you.